Yeah. Oh, great. Okay. Well, I'm just read the first sentence from my thesis acknowledgement. I am enormously grateful to my supervisors, Rick, Millane, and Phil Bones, for all their time, guidance, stories, and friendship. Their enthusiasm for what they do in academia and in life is truly inspirational. Go.
Okay, thanks, Joe, and good morning, everyone. It's morning here. I'm not sure what time zones people are in. So Joe asked me to give a talk, and I saw this illustrious group of speakers, and was wondering what I could add to that. So if I can get this thing going. Okay, so in thinking about that, what I decided to do was just to spend a little bit of time talking about the discrete Fourier transform. So we normally describe diffraction by the Fourier transform, and we use a discrete Fourier transform when we come to do the actual calculations. However, in the case of crystallography, if you work with the discrete Fourier transform directly, then that can be sort of informative as to what's going on. So I thought I would talk a little bit about that, and then also something about using that to look at properties of the phase problem for two-dimensional and one-dimensional crystals. Okay, so we have sort of two cases: single particle imaging, where we have a single object diffracting, say, X-rays, and we measure a continuous diffraction pattern. And then we have crystallography, where we have a crystal diffracting X-rays, and we measure a diffraction pattern, and that is the Fourier transform of one molecule, the contents of one unit cell, sampled on the reciprocal lattice. So we'll take a look at both of these, but focusing primarily on the crystallography case. Okay, so in the excuse me, the single particle imaging case, or diffraction in general, we normally describe by the Fourier transform, which is this equation here, and rho of x is the electron density of the object, and f of q is the complex diffraction pattern. Now, let's take a look at the discrete Fourier transform. So the discrete Fourier transform is used for describing the Fourier transform of a sampled object. And in developing the discrete Fourier transform, we assume that that sampled object is periodic. So, can you see my mouse? Joe?
Yeah. When you move it, I think it appears.
Oh, okay. I'll keep moving.
Yeah.
Does it disappear when it stops?
No, it's good now. Oh no.
Yeah, it has disappeared. Yes, okay. I don't know what the reason for that is. Okay, so here we have a one-dimensional sampled object, and the brown box here indicates one period of that sampled one-dimensional signal. Okay, and so the red dots are samples in one unit cell, and the green dots are the same thing in the next unit cell of the next period, and this repeats infinitely. So if we take the Fourier transform of that infinite periodic sampled object, then the Fourier transform reduces to the discrete Fourier transform, and this is the equation for the discrete Fourier transform. And now rho of m is a sampled electron density in one unit cell or one period, and there are large m such samples in one period, and Fn is the Fourier transform of this object, infinite object, and it turns out that that is sampled. Okay, so rho m is the samples of the electron density, Fn is the Fourier transform. Okay, now it turns out that the discrete Fourier transform is also sampled and is also periodic. So it looks a bit like the object. And one period of the discrete Fourier transform represents a diffraction from the whole periodic object. Okay, so if we think about that, then the DFT is perfect for describing diffraction from a crystal, because a crystal is periodic, and the DFT describes the diffraction by a periodic object. The electron density is sampled, maybe not physically, but in practice, it's sampled in the computer. And so then one period of the DFT, this set of samples here, are then the structure factors of the crystal. So the DFT is perfect actually for describing diffraction by crystals, as well as being the practical computational implementation of the Fourier transform. Okay, so I described that in one dimension, but of course that applies in 3 dimensions as well. So let's just take a look at that. So let's say we have a unit cell that has n by n by n samples. Then the DFT will have n by n samples, and that represents the diffraction on the reciprocal lattice of a crystal with this unit cell. And we can use that to look at the number of data and the number of parameters if we want to infer the contents of the unit cell from the diffraction pattern. So the unit cell has n by n by n or n cubed parameters, and the diffraction pattern has n by n by n or n cubed data. Okay, because the number of samples in one period of the DFT is the same as the number of samples in one period of the object. Okay, so we've got n cubed data, but each datum has an amplitude and a phase. So we have 2n cubed data, but we have Friedel symmetry, so only half of them are independent. So we've got to halve that again, and we have n cubed data. So we've got n cubed parameters and we've got n cubed data. So there's just enough data to reconstruct the electron density in terms of the data parameter ratio. So let's look what happens when we lose the phase. Okay, so the contents of the unit cell are the same. We have n cubed data, but we don't have an amplitude. So now we don't have the phase, so we only have n cubed data, but we still have the Friedel symmetry. So we need to divide that by 2. And so we have n cubed over 2 data, and we have n cubed parameters. Okay, so we have only half the number of data is what we have parameters. And so the solution to the phase problem is highly non-unique. So that's maybe another way at looking at the uniqueness of the crystallographic phase problem. Now, just taking an aside, if we had a single object, so now this is an isolated object, so this is not a unit cell and it's not periodic, then you can show that that's equivalent to, or the diffraction is equivalent to taking the DFT of that object and sampling it at twice the rate. So with an extra sample between each Bragg sample. And if we look at the data parameter ratio, we now have 2n by 2n by 2n data. So we've got 8n cubed. We still have Friedel symmetry, so we have 4n cubed. So now we have 4n cubed data and n cubed parameters. So we have plenty of data. We have, in fact, 4 times as much data as what we need. And so we expect a unique solution in the case of single particle imaging. And we know that that is quite feasible to reconstruct single particles from their diffraction amplitudes alone. So summarizing this then, if we call omega the data to parameter ratio for the problem, then for a crystal we have half the number of data that we need. So the data parameter ratio is a half. For a 3D object, is 2n by 2n by 2n divided by 2 over n cubed is 4. And it turns out for a 1D object and a 2D object that the data parameter ratios are 1 and 2. So the degree to which the problem is overdetermined increases with the dimensionality, in fact, for single particles. For a crystal, it doesn't matter. Well, yeah, actually it does matter. Just forget that. So given this data parameter ratio, how many data do we actually need? So if we had a linear problem and it was ideal and no noise, then if we have the same number of data as what we have parameters, then in principle, we could solve for the unknown. So that's like if you have a system of n linear equations and n unknowns, then there's a unique solution. And so in principle, omega equals 1 is sufficient. However, we don't have a linear problem when we are measuring the amplitudes, because although the structure factors are a linear function of the electron densities, the diffraction amplitudes are not a linear function. And because the problem is not linear, we're going to need more data than if we had the linear case. But it's not highly nonlinear, so actually you don't need much more data to still get a unique solution. So as long as omega is a bit greater than 1, in the ideal case, then that should be sufficient for a unique solution. Now, of course, in practice, you need somewhat more data because you've got to compensate for the effects of errors and data incompleteness and all of these things for which additional data helps compensate. Okay, so that's sort of a summary of the uniqueness properties or the crystallographic phase problem looked at from the perspective of the DFT. So I thought it would be interesting to look at the case of a 2D crystal and a 1D crystal. So let's consider the case of a 2D crystal. So 2D crystals have been used for structure determination, primarily in electron crystallography. And there's also been some work using X-ray free electron lasers to collect data from 2D crystals. So we can, using the DFT, we can take a look at what the uniqueness properties are for if we measure the diffraction amplitudes from a 2D crystal. Okay, so a 2D crystal is periodic in 2 dimensions, but finite in the 3rd direction. Okay, so that's illustrated here. We have a sample which is periodic in 2 directions, but is finite or 1 molecule thick in the 3rd direction. So that means that the diffraction is going to be sampled in the 2 lateral directions. Okay, because we have periodicity, so we have Bragg sampling in those 2 horizontal directions, but we'll have continuous diffraction in the 3rd or vertical direction. Okay, and that's illustrated down here. In reciprocal space, we measure diffraction continuously along these lines, but we have sampling, Bragg sampling in the 2 lateral directions. So these lines are spaced by the Bragg spacing in the 2 lateral directions. And these things here are sometimes called Bragg rods, and we measure diffraction on the Bragg rods. So using the DFT again, let's take a look at what that means. So we have now the unit cell of a 2D crystal, and if we take the DFT, so we're going to have, because this 2D crystal is periodic in the 2 lateral directions, we'll have samples of the Bragg spacings in the 2 lateral directions, so those are the green dots. But in the vertical direction, it looks like a single particle, and we saw that's equivalent to having additional data between the Bragg points. So that would be these red dots here. So for a 2D crystal, we sample the diffraction pattern in this way here. And so we can count up the number of samples and compare that to the number of parameters to get our data parameter ratio. So we're going to have, we have n samples across here. We have n samples across here. So we have n times n. And here we have 2n samples. So we have n by 2n divided by 2 for the Friedel symmetry, divided by n by n by n again for the number of parameters describing the electron density in the unit cell, and this reduces down to 1. Okay, so this shows that for a 2D crystal, the data parameter ratio is 1. So we sort of almost have enough data, but not quite enough to solve the phase problem directly. And if you look at this in a bit more detail, you find out that actually, in spite of, or maybe consistently with omega equals 1, there are actually many solutions that are admitted given this set of diffraction amplitude samples. And this is a simple example. So this is a small synthetic object, and so this is, I think, 8 by 8 pixels laterally and then 8 layers. So this is our 1 unit cell of a 2-dimensional crystal, and this is another 2-dimensional crystal, which is completely different to this one, and they both have identical diffraction patterns. So that's just an illustration of the fact that, you know, there are multiple objects for a 2-dimensional crystal that give the same diffraction pattern. Now you can reduce the number of redundancies if you have some envelope information, and so this is illustrated here. So this is 1 unit cell of a 1-dimensional crystal, and let's say you have some, I mean, the membrane protein, let's say you have some information on the upper and lower surfaces of the membrane. So that means that you know that the electron density is 0 in these regions outside the membrane, and that forms a support constraint, like Jeff mentioned, that constrains the solution. And without going into a lot of detail, you can show that if the region excluded divided by the volume of the unit cell is greater than the resolution divided by the thickness of the unit cell, then you expect a unique solution. And I've just got an example here. If 20% of the volume was excluded, for example, and you had 3 angstrom resolution data, and a 50 angstrom thick membrane, then this will be 0.06, and 0.2 is greater than 0.06, and so in that case you'd expect a unique solution. Okay, and this is just showing that you can sometimes get some information on the structure of the surface by, for example, atomic force microscopy. So we did some simulations of ab initio phasing. And we're going for time, Joe.
Hold on, let's see. Yes, you have 3 minutes.
3 minutes.
Yeah.
3 minutes to go, or?
Yeah.
Oh, okay, right. Okay,
But
so
take your time, don't worry.
So we did some simulations using aquaporin, and we generated diffraction data from 2D crystals. In this case, the membrane thickness is 60 angstroms. We did it at 4 angstrom resolution, and we had an envelope that was at about 10 angstroms resolution. and we put noise on the data so that I over sigma was about 5 in the highest resolution shell. And then we used one of these iterative reconstruction algorithms that Jeff talked about to reconstruct from a random starting density. And with this sort of level of noise, we could reconstruct the electron density. And I'll just show that in here. So this is the envelope that we used. This is the true density at 4 angstroms, and this is the reconstructed density. And I've just got a note here. There's been some work by some people at PSI in Switzerland, and they measured diffraction data from 2D crystals of purple membrane, and analysing SNR, and extrapolating their results indicates that you could get this sort of level of this sort of signal level with about 400,000 index diffraction patterns if you're working at 3 angstroms resolution. So, you know, it looks sort of feasible in terms of ab initio phasing from 2-dimensional crystal data collected in XFEL. Right, and so finally, just want to mention the case of a 1-dimensional crystal. And I've got a picture here of DNA, which is an example of a 1-dimensional crystal. And so the key thing here is that you have a molecule or assembly that is periodic along 1 dimension, but is a single molecule wide in the lateral directions. And there are many examples of such systems in biology. I've mentioned microtubules, flagella, rod-like viruses, muscle proteins, nucleic acids. So there are a lot of systems in biology, filamentary type systems that can form 1-dimensional crystals. And so there's potentially opportunities for measuring diffraction directly from single 1-dimensional crystals for structure determination. So the 1-dimensional crystal is now finite in 2 directions and periodic in the 3rd direction. Okay, so that means that the diffraction is sampled along 1 direction. So if you look at the DNA here, then we have sampling along this axial direction here, and we have continuous diffraction in the lateral direction. So that means that we measure the diffraction continuously on planes that are separated by the Bragg spacing. Okay, and these are often called layer planes. So in principle, if we could isolate single 1-dimensional crystals in the XFEL focus, and we could make measurements and then assemble those with sufficient SNR, we could potentially measure this collection of diffraction amplitudes in reciprocal space that is continuous in 2 directions and sampled in the other. So we can use our DFT description again. So once again, we've got the unit cell of a 1-dimensional crystal, and the DFT describes the diffraction. And now we have, because the crystal is periodic in the vertical direction, we have Bragg spacing in the vertical direction, the green dots, and in the 2 lateral directions where the assembly is 1 molecule wide, we have these extra samples between the Bragg reflections. And so we can count up the data to parameters again, and we have n by 2n by 2n divided by 2 for the Friedel symmetry, divided by n cubed parameters described with the density in the unit cell, and we get omega is equal to 2. So that's a fairly nice number because it's quite a lot bigger than 1. And so there should be ample data to solve the phase problem directly. But again, there are actually some multiple solutions, and this just really comes about because this arrangement of the samples of the Fourier transform is very structured. If these were scattered around randomly, then you'd be in very good shape. But because they're structured in this way, and you have these sort of big Bragg spacing gaps between the planes, that does admit some multiple solutions. And so again, that's illustrated here. So this is again showing sections through the unit cell of a one-dimensional crystal. And this is another one-dimensional crystal, and both of these have identical diffraction patterns. So that's an illustration of the existence of multiple solutions to the problem, although the data parameter ratio omega is equal to 2. However, although there are these multiple solutions, the set of these multiple solutions is very small compared to the overall number of possible electron densities. So it doesn't take much additional information to eliminate these other solutions. And in fact, you can show that if you have some envelope information and that envelope information deviates from a cylinder, then that eliminates the rest of the solutions. So if you have some envelope information that is different to a cylinder, so this is the envelope of one unit cell of the crystal, if that deviates from a cylinder, then there's a unique solution. And of course, in practice, the more it deviates from a cylinder, the easier that solution would be to find. And so I'll just finish up with some simulations that we've done, or my colleague Millane has done, of ab initio phasing from diffraction data from a 1D crystal, and for this we used BDNA. So we took one unit cell of 1C repeat of BDNA, calculated data that would be collected from that would be generated from a 1D crystal. The data were between 20 and 2.5 angstroms. SNR of 2 in the outer shell between 3 and 2.5 angstroms. Started with a cylindrical envelope and then used the shrink wrap algorithm. And in IPA, and once again in the same way that Jeff described, starting with a random electron density, and we were able to reconstruct the electron density of DNA, which is shown here, and this shows the molecular model of a couple of base pairs in the sugar phosphates. Now, one problem with one-dimensional crystals is that the diffraction is going to be extremely weak because you're only getting coherent amplification from unit cells along one direction. So you're going to have, in practice, a very small number of unit cells compared to the number of unit cells that you have in a one-dimensional crystal. And we've done some sort of rough calculations that indicate that you need 10 to the 6 to 10 to the 7 patterns in order to be able to average up to get this sort of SNR. So that will be challenging, but instrumentation has a remarkable way of sort of improving beyond what you might expect. So it may be feasible, in the near future to measure diffraction patterns from such specimens and be able to extract good enough data to do reconstructions. So I'll finish up there. Just summarize by saying that the discrete Fourier transform aside from being useful for computation, is also useful for understanding properties of the phase problem crystallography, and that with intense X-ray sources such as free electron lasers, direct phasing may be feasible from diffraction data collected from 1D and 2D crystals. Right, thank you. Any questions?